You know, for over 2,000 years, one single book was basically the gold standard for how to think, how to argue, and how to prove something was true. It's called Euclid's Elements. And yeah, you might think it's just a dusty old geometry book, but its real story is about something way, way bigger, the very architecture of reason itself. So let's dive in and take a look at that blueprint.
I want you to think back to high school geometry class. Remember all those triangles and circles? All that work with a compass and a straight edge, trying to write those two-column proofs? It probably felt like just a random collection of facts about shapes. But what if I told you the real lesson, the most important part, was completely hidden in plain sight?
And that right there is the key. The most revolutionary part of Euclid's Elements isn't what he proved, but how he proved it. This book is an absolute masterclass in a powerful method for building certain knowledge from the ground up, and it's a method that would literally change the world.
All right, so to really get this, we've got to break down Euclid's blueprint. We're going to look at the system he created, piece by piece, and see how he built an entire universe of knowledge from just a handful of simple starting ideas.
The secret sauce, the engine behind this whole thing, is what's called the axiomatic deductive method. And the idea is just brilliant in its simplicity. You start with a few statements that are so ridiculously obvious you don't even need to prove them. Those are your axioms. Then, using nothing but pure, cold, hard logic, every single other truth in the system can be derived from that simple foundation. It creates this unbreakable chain of reasoning. And a crazy thing is just how simple and clean this foundation is. Euclid started with 23 definitions, basically to make sure everyone was on the same page, speaking the same language. Then came the axioms, and they came in two flavors. 5 postulates, which are the basic rules for doing geometry, and 5 common notions, which are just universal truths, like the whole is greater than the part. And that's it. That little handful of ideas is the entire bedrock for hundreds and hundreds of proofs.
Okay, so that's the theory, right? But to really see the magic, you've got to see this engine in action. So let's take one of the most famous results from the Elements, you've all heard of it, the Pythagorean theorem, and see how Euclid proved it, not with algebra, but with pure geometric logic built right from his axioms.
And honestly, the way he does it is it's a work of art. First, he builds squares on each side of a right triangle. Then, and this is a clever move, he splits that big square on the hypotenuse into 2 smaller rectangles. Now here's the genius part. Using rules he'd already proven, he shows that the area of the first little square is a perfect match for the area of the first rectangle. Then he just does the exact same thing for the other side. So what's the conclusion? It's inescapable. The 2 small squares have to add up to the big one. No numbers, no a squared plus b squared, just pure visual deductive logic.
But there was a catch. One little piece of Euclid's otherwise perfect system just didn't quite fit. One of his 5 postulates wasn't like the others, and it launched a mystery that would obsess the world's greatest minds for the next 2,000 years. I mean, just look at the difference here. It's night and day. Postulate 1 is so simple, so elegant, to draw a straight line from any point to any point. Of course. But then you get to the 5th postulate, and it's this complicated paragraph about what happens to lines that go on forever. It just feels less like a self-evident starting point and more like something you should have to prove.
And it wasn't just us thinking it was weird. Mathematicians agreed. For 2,000 years, the smartest people on the planet tried to prove the 5th postulate using only the other axioms. Even Euclid himself seemed a little suspicious of it. He avoided using it for the first 28 propositions. From ancient Greece to the Islamic Golden Age, all the way to 18th century Europe, everybody tried and everybody failed.
So this epic failure, this 2,000-year-long struggle, it had to make you wonder, right? If nobody could prove it, did that mean Euclid's perfect system had a fundamental flaw? Was this one weird axiom a bug that broke the whole thing?
And the answer, when it finally came, was a total game changer. The 5th postulate wasn't a flaw. It was a choice. In the 1820s, a few mathematicians finally realized you could just deny it. You could say, nope, in my world, multiple parallel lines can go through a point, and logic didn't break. Instead, you created entirely new, perfectly consistent kinds of geometry.
This just blows your mind, right? The number of parallel lines through a point isn't a fact of the universe, it's a rule you choose for your system. It's like a setting in a video game. If you choose 1, like Euclid did, you get the flat, normal geometry we all learn in school. But if you choose 0 or infinite, you get these other wild, curved geometries, worlds where the rules are different, like on the surface of a sphere. The 5th postulate wasn't a truth, it was a dial you could turn to create a whole new world.
And that idea, that you can build entire universes of thought just by changing a few starting rules, that's the real legacy of Euclid.
This blueprint for thinking would go on to shape fields way beyond mathematics.
So, fast forward to the 17th century. You've got this philosopher, Baruch Spinoza, and he's looking at Euclid's method and thinks, wait a minute, what if I could use this for philosophy? He wanted to tackle the biggest questions, God, reality, ethics, with the same rock-solid certainty as a geometric proof.
And he wasn't kidding around. He did it literally. His masterpiece, Ethics, is structured exactly like Euclid's Elements. It starts with definitions of God and substance. It lays out axioms he thought were undeniable. And then, step by logical step, he derives hundreds of propositions, each with its own formal proof. It was this breathtaking attempt to make philosophy as rigorous as math.
And at almost the exact same time, another absolute giant of science was doing something very similar. Isaac Newton was a huge admirer of Euclid, and he totally got the power of deriving massive complexity from just a few simple principles.
You look at Newton's masterpiece, the Principia Mathematica, the book that laid the foundation for modern physics, and what do you find? It's the same blueprint. It starts with definitions for mass and force. It lays out his 3 laws of motion as axioms, and then he logically deduces his law of universal gravitation as a theorem. He literally built his entire physical universe on top of Euclid's logical foundation.
Okay, so Euclid shaped philosophy, he shaped science. That's amazing. But why on earth do we still have to do proofs in high school geometry? Well, once again, I'm going to tell you, it's not about the triangles. It is a powerful, structured way to train your brain to think with clarity and precision.
Well, there's actually a really cool model for how our brains learn to think this way. It shows that we all go through these levels. We start by just seeing shapes. Then we learn their properties, like a square has 4 right angles. Then we learn to relate those properties. But the highest level, the peak of this stage of thinking, is formal deduction. The ability to build a logical proof inside a system, just like Euclid's. Learning to write proofs is literally the process of climbing this ladder of abstract thought.
And that's the whole point, isn't it? The real value of wrestling with Euclid's system isn't memorizing theorems. It's about forging these incredible cognitive skills. Logical reasoning, critically examining your assumptions, and building a solid, step-by-step argument. These are skills for life, not just for a math test.
So we kind of end up right back where we started, the architecture of reason. Euclid's greatest gift wasn't geometry. It was a method for understanding our own assumptions, our axioms, and seeing the worlds they create. And that forces us to ask a really big question. In our laws, our ethics, our science, what are the fundamental, unproven axioms we've chosen? And what kind of worlds have we built on top of them?